In this video, we are going to look at graph colorings. And so as we look at graph colorings, we're going to define what this is, we'll identify the chromatic number, and we'll talk about some important results in graph theory that show up with colorings. As we look at this, let's define what we mean by a proper coloring. So when we refer to a proper coloring, when we talk about a proper coloring, if G is a graph with no loops or multiple edges, any assignment of colors to the vertices of G so that every pair of adjacent vertices have different colors is called a proper coloring. Right? So imagine that we have some graph, and maybe our graph looks like this. So maybe this is our graph. We want to know what is a proper coloring for this graph. And so as we go through, we could go through and we could give this one color. We could give that a different color. This one's not next to the first pink one, so we color that same color. We could not color this one pink or blue, so we can give it a color of green. You could give this one a color of orange. We could go back to pink if we wanted, and then we could give this blue. And so we could color that with 4 different colors. As it turns out, 4 is the fewest number of colors that we would need to color this properly. So you could not, it's impossible to color this with fewer than 4 colors. We can see that when you look at this set of vertices right here, this vertex is next to all of those other 3, and those other 3 are also pairwise next to each other. And so what we really have there is we have this complete graph on 4 vertices that shows up, and so each one of those is going to be required to have a different color. And so that is the fewest number of colors. Notationally, we use the Greek letter chi. Chi of G, the chromatic number for this graph, is equal to 4. Now I just used a term that you're not familiar with, or you may not be familiar with, and that's the chromatic number. So let's define that. The smallest number of colors that are needed to obtain a proper coloring of G is called that chromatic number, and we denote it with chi of G. And so let's say we have this graph here. Oh, and I don't know, maybe we'll have another graph over here. We'll look at the coloring for each of these. So for that first graph that I drew, we could give this a color of pink. Right next to it, you have this one. This one down here, it cannot be pink. It also cannot be orange, so it has to have a different color. So let's give it a color of green. And then that last one, we could color that one pink again. And it turns out that is the best that we could do for this graph. So its chromatic number, chi of G, it is equal to 3. On the second graph that I drew, you could color that pink. Right next to it, we could color that blue. The one next to it, we could go back to pink because it is not directly adjacent to the first pink one. And then we could go back to blue. And then we could go back to pink. And then we could go back to blue. So we could just alternate colors. And so it does turn out on this one that the chromatic number, chi of g, it is equal to 2. So associated with coloring of graphs, we might color maps. And so if we were to look to color a map, let's say we have this map of the US. A map is colored properly if no two regions sharing a common border other than that's more than just a single point have the same color. Right? So it's okay here they meet at a single point, and so this state here could have the same color as this state here. So those could have the same color because they meet at a single point. But next to it, this would have to have a different color because it borders it. This would have a different color. It could have the same color as that one to the north and east of it. And we're just going to go through and we want to try to color this thing. So we're coloring. As you go through and color this thing, there's a variety of colors that you might use. But the question shows up, what is the fewest number of colors that you could use? Right? So how few colors do we need in order to color this map of the US? And as we keep going through, you could just color and color away. And how many colors do you think it's going to take? How many different colors? And we have 50 states. Feels like we might need a lot of colors. So far, we've done everything up to this point with just 4 colors. Do we need more than 4? Can we do this with only 4 colors? And so that's a really good question. It's a question that mathematicians looked at and considered for a while. As they considered this question, the computer was in its early stages, and so someone started to explore this using a computer. So that someone was Apple. So let me, oh man, did I make a poor decision? Ooh, I might have made a poor decision. Let me flip-flop something. Make that pink, maybe that green, and that pink. Orange here. And down here in Louisiana, we could have it be green. And so as you continue going through this, what you will find, what mathematicians eventually found, was that we could color the entirety of this map with just 4 colors. Now, there is a quick note that each state must be a connected region. And you could make a crazy map and find the fewest number of colors. And no matter what map you make, as long as it satisfies this, each state is a connected region, it will be, you could color it with 4 colors or fewer. So the 4-color theorem says only 4 colors are required to color any map drawn on a flat surface. It has never been proved by hand. But Kenneth Appel and Wolfgang Haken, they were able to prove this using a computer. It was the first major theorem to be proved using a computer. There was not everyone accepted it because it used a computer. So it was pretty interesting. Now, part of what showed up here is in this theorem, a more formalized version of this theorem, requires us to define another type of graph. And so we will do that in our next video. I will see you there.